In the last chapter, chapter 11, we found out that most stars, like our sun, for example, end in the white dwarf phase. They end as a burned out core of a star, a hot, white hot ball of carbon after the red giant phase. That's the end for most stars. Explode, that's always more exciting. First, we're going to look at something called a nova, a pretty rare event. For a nova to occur, you have to have a very particular situation. You have to have a white dwarf, in other words, a star that's gone through its entire evolution to the white dwarf phase, in a close binary system where that white dwarf is now sucking over material from its partner star in a mass transfer. Now, a mass transfer is going to be hydrogen, helium. It's going to be a normal star, maybe in the red giant phase, for example, and hydrogen and helium are pouring over onto this white hot ball of carbon called a white dwarf. Well, it's a little bit like dropping water on a hot skillet and watching it sizzle. That white dwarf is plenty hot enough to fuse hydrogen helium. Now, the hydrogen helium doesn't pour directly on. It actually swirls around, kind of like material going down a bathtub drain. And that disk of material that forms around the white dwarf is called an accretion disk. Material heats up so much it can actually give off high-powered radiation like ultraviolet and X-rays. And this will become important later on when we talk about black holes. But for now, as the material pours onto the white dwarf, it can ignite surface fusion. The white dwarf itself isn't fusing, but again, like water on a hot skillet, when that hydrogen pours over onto that super hot white dwarf, it will fuse. It will blow up from the surface. It will flare up and become a million times brighter. Now, astronomers don't see this happen too often. They only see a few of these per year anywhere in the universe, so it's a very rare event. Now, this is very interesting because the same white dwarf can do this over and over again. We're going to watch a video here of what's called a recurring nova. So let's watch as this process takes place more than once. So we start out here with the star, let's say, perhaps in its red giant phase, materials pouring over across the Lagrange point, the L1 point, and forming this accretion disk right here around the white dwarf. So that material is pouring over, building up pressure, and then you're going to have a surface explosion right there. That is the nova, that flare up. Some of the material is kicked into space, and then immediately a new accretion disk begins forming. There's an example of one of these that we have, astronomers have watched for about a century now, and about every 30 in a nova explosion. So that's a recurring nova. But this doesn't happen forever. Instead, the recurring nova, every time it happens, the white dwarf, it gains a little weight. It adds a little mass. And a long time ago, a physicist named Subrahmanyan Chandrasekhar, a contemporary, sometimes I think partner with Albert Einstein, he was on a ship from India to England, and he realized, using some calculations, that a white dwarf has a maximum mass. And this is a pretty nice set number in astronomy, kind of a rare thing where you have a very solid number. And the number he came up with was 1.4 times the mass of our sun, 1.4 solar masses. A white dwarf cannot be any heavier than that. Why? More mass means more gravity. More gravity means more pressure. And at 1.4 solar masses, there's enough pressure there to fuse carbon. And what is a white dwarf? It's a ball of carbon. So at that point, it's like a firecracker going off. It's like gunpowder. Once it ignites, boom, that is it. The entire thing is destroyed. The entire thing blows up in what we call a Type I supernova. It's going to be very, very different than a Type II. And when a Type I blows up, one way that they know it's a Type I is because the spectrum will be simpler. It was a ball of carbon. It's not going to have as much hydrogen and helium and other elements as what a Type II is going to have. So we'll find out about Type II supernovae in the next lecture. Thanks for listening.